What specific problem does the proposed dynamic 10H DYT method aim to address in the context of normalization layers within transformer architectures?
The proposed dynamic 10H DYT method aims to address the reliance on normalization layers, specifically layer normalization (lane), within transformer architectures. The paper highlights that lane layers, while effective, require the computation of activation statistics, which can be cumbersome and may not be necessary for stable training. DYT emulates the behavior of lane by using a learnable scaling factor, alpha, and the bounded 10H function to squash extreme values without needing to compute these statistics. This approach not only simplifies the architecture by allowing for a direct replacement of normalization layers, but also maintains comparable performance and stability during training. Additionally, DYT is designed to improve training and inference speed, making it a more efficient alternative for modern neural network design.
How does the proposed dynamic 10H DYT algorithm work? Illustrate its operations step by step, including the role of the learnable parameter alpha.
The proposed dynamic 10H DYT algorithm operates as a drop-in replacement for normalization layers in neural networks, specifically designed to emulate the effects of layer normalization (lane) without computing activation statistics. The operation is defined as DYTX equals gamma CDOT 10H alpha CDOTX plus beta, where gamma and beta are learnable parameters that allow the output to be scaled and shifted similar to normalization layers. The key component, alpha, is a learnable scalar parameter that dynamically adjusts the scaling of the input, x, based on its range, effectively controlling how aggressively the 10H function squashes extreme values. This means that as alpha changes, it influences the steepness of the 10H curve, allowing the model to adaptively manage the input's variance. Overall, DYT preserves the nonlinear squashing effect of normalization layers while simplifying the computational process by eliminating the need for mean and variance calculations.
Can you provide a simple yet illustrative example that walks through the main algorithm steps of dynamic 10H?
Dynamic 10H DYT operates as a drop-in replacement for normalization layers by applying a specific transformation to the input tensor. The main algorithm steps are as follows. First, given an input tensor, x, the DYT layer computes the output using the formula DYTX equals gamma CDOT 10H alpha CDOT x plus beta, where alpha is a learnable scaling parameter, and gamma and beta are learnable affine parameters that allow the output to be adjusted to any scale. The learnable parameter, alpha, dynamically adjusts the scaling based on the input's range, which is crucial for maintaining performance. This operation is performed independently for each element in the tensor, thus preserving the nonlinear squashing effect of normalization layers without requiring the computation of activation statistics. Finally, DYT can be seamlessly integrated into existing architectures by replacing normalization layers, ensuring that the overall structure and other activation functions remain unchanged.
What theoretical or practical benefits does dynamic 10H offer compared to traditional normalization layers like layer normalization, lane, or RMS norm?
Dynamic 10H DYT offers several theoretical and practical benefits compared to traditional normalization layers like layer normalization, lane, or RMS norm. Firstly, DYT eliminates the need to compute activation statistics, which simplifies the training process and reduces computational overhead, leading to faster training and inference speeds. Empirically, DYT maintains performance comparable to lane while requiring minimal tuning of training hyperparameters, making it easier to integrate into existing architectures. Additionally, DYT's learnable parameter, alpha, allows for dynamic scaling of inputs, which helps in squashing extreme values effectively without the complexities associated with traditional normalization methods. Overall, DYT serves as a straightforward drop-in replacement that preserves the benefits of normalization while enhancing efficiency and stability in training.
How was dynamic 10H validated or tested in the experiments? Discuss the experimental design, datasets used, and metrics for performance evaluation.
Dynamic 10H, DYT, was validated through a series of experiments involving transformers and other modern architectures, where it replaced layer normalization, LANE, or root mean square normalization, RMS norm, in the original models. The experimental design followed official open-source protocols for training and testing, ensuring that hyperparameters were kept identical to those used in the normalized counterparts, which facilitated a fair comparison. The models were evaluated across diverse tasks and domains, including a specific long-range DNA sequence modeling task using the human reference genome data, where DYT maintained performance comparable to LANE. Performance metrics were not explicitly detailed in the provided text, but the results were presented in tables comparing DYT's performance against LANE and other methods, highlighting its effectiveness and efficiency. Additionally, the experiments included analyses of computational efficiency, demonstrating that DYT significantly reduced computation time compared to RMS norm layers.
What significant results were achieved using the dynamic 10H method, and how do they compare to previous methods in terms of performance?
The dynamic 10H, DYT method demonstrated significant results by maintaining performance comparable to layer normalization, LANE, in various tasks, including long-range DNA sequence modeling, while also improving training and inference speed. Empirical evaluations showed that DYT consistently outperformed other methods aimed at training transformers without normalization layers, such as fix-up and skip-init, which required lower learning rates to prevent divergence. Additionally, DYT achieved stable training without the need for extensive hyperparameter tuning, unlike previous methods that often necessitated adjustments to initial parameter values or weight constraints. The results indicate that DYT not only preserves the benefits of normalization layers, but also enhances computational efficiency, making it a promising alternative for efficiency-oriented network design. Overall, DYT's performance across diverse configurations highlights its effectiveness compared to traditional normalization techniques and other contemporary methods.